It's halfway here. I'll give you that one of those. I don't want it back.
Is the screen show the presenter view again?
I don't know. We almost have to go to it to figure out what it's going to do. I can never figure it out.
F5.
So we're going to
Everyone, our first speaker this afternoon is Josiah McClure. Josiah is a second-year graduate researcher here at UIUC working with Dr. Palawa. He received his BS and MS degrees in electrical and computer engineering from the University of Iowa, where he graduated with highest distinction and received 1 patent for an implantable medical sensor. He is a recipient of numerous scholarships and awards, including the National Science Foundation Graduate Research Fellowship. He deeply regrets that he didn't have time to bring any cookies for this talk, as baking is his most important qualification.
All right, thank you, Serene. So my talk today is about, it's entitled A Series Stacked Architecture for Highly Efficient Data Center Power Delivery. And as is illustrated on my beautiful title slide here, the way that power is delivered, basically what we're going to talk about today is the world's first implementation of a series stacked server cluster, which is a different way of delivering power to servers. I don't think I really have to spend a lot of time convincing all of you that the internet is important. But what you may not be aware of is that the physical infrastructure that supports the internet is becoming increasingly difficult to power. One of the reasons for this is that the power density of data centers is going up, 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 up. To give you an idea of how much up, last year, the average data center across the globe used about 2 megawatts, which is an industrial scale load, all packed into a relatively small data center. So, how is power currently delivered to data centers? And how does this affect the overall losses of the data center? Well, I could go on and on about the specifics of where power is lost in a data center and how electrical conversion losses tie into that. But I thought it would be better to just have you take my word for it that the electrical conversion losses represent a significant portion of total data center losses and they affect the other losses within the data center. So how is power currently delivered? Basically, it's the same way that power is delivered to your computer in your office. You have each server in the data center will have a single power supply. That power supply will be plugged into the wall. All the power that goes to the server goes first through the power supply and is subjected to the associated losses of that power supply. Our proposed architecture, the series connected architecture, instead of first passing all of the power through the power supply, it will allow the energy to flow directly from a distribution bus successively through each server. That's why it's called series connected architecture. And of course, whenever you have series connected loads, you're going to have to deal with some kind of voltage regulation. So there will be some losses associated with voltage regulation, but those losses will be smaller. How much smaller will they be? Oh, also, I made sort of more circuit-y pictures for those of you who didn't like my previous slide. Right, so the current architecture, you have your distribution bus here, you have power supplies. Each one of those power supplies has some certain efficiency. In our proposed architecture, you have a single DC distribution bus. You have all the servers connected in series. And you have some regulation hardware that also has some certain efficiency associated with it. And you can run some simulations. Basically make some nice assumptions like the distribution of server power is Gaussian. Turns out this is a good assumption because of the way that loads are scheduled, or jobs are scheduled within the CPU. And we have some data to support this. So anyway, you run these simulations, and with a certain regulation hardware topology that we picked, we got over 8 times reduction in power losses with using the same efficiency of converter. So just by rearranging the power cords in your stack, you're able to get an 8 times reduction in loss. So it sounds great. Oh, this is just if you care about the details of the simulation. I don't think you do. So can we do even better than that? The answer is yes, if you're intelligent about the way that you schedule your loads. So shown on the, I guess it's right here, is sort of the case that I talked about previously, where you have some certain distribution of loads for all of the servers. And that would be similar to, in a typical data center, you have one single central load balancer. So all the traffic is coming into your data center. And it gets sort of balanced between all of the servers in the data center indiscriminately. And so you end up with some certain standard deviation of power between the servers. Now, instead of having one central load balancer, you have in between, let's say at the top of each rack, you have a rack load balancer that takes into account, basically it acts like a filter. So what the rack sees is loads coming in with similar CPU usage and power profiles. So if you can do that, you can reduce the variation in server powers and end up with significantly reduced power being processed. All this sounds like, oh yes, go ahead.
On this slide, so what sort of impact does this have on latency, right? Like if you have a really low latency application, you're inserting some extra work between the load coming in and getting processed out to the individual servers. So like, is it going to add a lot of latency and then cause service issues?
Yes. So this is a really good question, and we're still doing some studies to figure out exactly what kinds of applications this is applicable to. And even, I mean, the other thing that I didn't really mention here is getting this very small standard deviation is actually really hard, because you have to make estimations of how much power a certain job is going to take, and you want to do that estimation very quickly. So yeah, it's still an open question as to how much this will work, but I have some actual experimental results later on that will sort of shed some more light on this. So, but good question, thanks. Right, so sounds great. Let's hit the lab. Let's actually try to make this work. And as I promised at the beginning, or as I talked about a little bit at the beginning, the really cool thing here isn't the big idea. The big idea is relatively simple. The cool thing is that we're the first to make it actually work. And I'll talk about briefly how we did that. Step number 1, we want to compare apples to apples, essentially. When you do your comparison between this architecture and this architecture, you want to compare the same thing. Second, I'll talk briefly about how we made this work. I'll talk about the hardware that we built to manage the voltages. And last, I'll talk a little bit about the intelligent scheduling that we designed. So, how do we compare apples to apples? It's really hard when you're dealing with inherently variable loads like servers. It's really hard to make a fair comparison. One way of doing this would be to do sort of a statistical study where you run the experiment many, many times and get sort of a confidence interval and do all of that. The other way is to reduce the variance between your experiments, and the way we did that, and we chose that way, basically what we did was we ran certain jobs on each server, whether it was configured in the parallel stack or the series stack, and we would record that power consumption, and then we would play it back on electronic loads. So we had electronic loads basically doing exactly the same thing as was done in the parallel case or the series case, depending on where we took the measurements. That's how we did our comparison. Let's talk, I don't know how much time I have left. Okay. Let's talk briefly about what we did to manage the voltages between, manage each server voltage within our stack. So the methodology that we used for voltage regulation is a technique called differential power processing, which I'm sure a lot of you have heard, especially in the solar realm. There are a number of ways of doing this, different topologies that you can use. The one that we chose was called element-to-element topology. And I don't really want to get into all of the technical details of why we chose this over, say, element to virtual bus or element to bus, etc. But the nice thing about this topology is that it's straightforward to design. Basically, no need for isolation, so we don't have to worry about transformers. Also, the control can be fully local, especially in the case where each server voltage has to be balanced, which is the case in our server setup. There doesn't need to be any communication between each module. So that's pretty nice. You can just program your microcontroller, set it to go, and it just only looks at its own voltage readings, and the whole stack gets balanced. The other nice thing is that there's very low voltage stresses on these switches, so they can be really high efficiency. Right. As far as actually designing the converter, we chose to use sort of four-phase interleaved buck-boost topology, which basically 4 phases allows voltage ripple to go down and makes it so that our inductor can be sized very small for a low amount of current. Right. Okay. So the last thing I want to talk about is this business of, so yes, we made it work, we balanced our stack, we're all happy to be the first one to do this. I want to talk briefly about the effect of balancing the load in software. So here's sort of this first case that we talked about where you have web traffic and it's coming in to a data center. In this case, we just have a 3-server data center, but it's a data center nonetheless. And we have a sort of central load balancer that's just giving traffic to each server indiscriminately. Like it will send one request to this server, send one request to this server, send one request to this server, and repeat. That's what round robin means. And you end up with this sort of profile where you can see in the parallel configuration, conversion losses are, conversion losses are relatively constant throughout the measurement, throughout the experiment. And that's because the efficiency of the converter between the wall and the server is basically constant throughout, the range of, what is that, 60 watts to close to 100 watts. In the case of the series configuration, you'll notice that there's quite a bit more variability in conversion losses as time goes on. But what you can notice is that really the only times when you have large conversion losses are these times when there's a step change in traffic or in CPU power consumption. And during that step change, the currents between each server are very unbalanced. And so that's why you have a large step change. But all the other times when they were being relatively balanced, you get relatively low conversion losses. What you can't see in this chart is that the variability, though, is pretty large. I had to do some averaging so that you could tell the difference, so that you could see green, red, and blue, so that they weren't covering up each other. So what we're going to see in the next chart is that you can get more reduction in losses by doing a better job at balancing not just the incoming traffic, but actually balancing the CPU on a fine-grained scale. So what you can do is get the server cluster to see itself not as a collection of distinct servers, but to see itself as one computer, basically, with 3 cores. So in your computer, let's say you have a four core, most computers nowadays have 4 cores. If you open up your task manager, you can see 4 different little windows that show CPU usage. The typical scheduler in most computers is to balance CPU consumption between all of those cores. And they do that by migrating threads between the cores. So if one core is being overloaded, they'll migrate some threads over to the other cores. And because there's a very high correlation between CPU usage and power consumption, you can use that same scheduler to balance the power consumption between 3 separate servers. You just have to do the tricky bit of getting the server to see itself as one system. And that's done through a distributed operating system. It's basically a collection of kernel modules that you compile into the Linux kernel. It's a real pain to get working. But once you do get it working, you get this very fine-grained control over power consumption within your cluster. And I slowed down the thread migration so you can see what's going on in this case here. Around 40 seconds, so it becomes idle. And then I start a three thread job. And so power consumption of server 1 goes up, and the rest of them remain low. And after a little while, the scheduler kicks in and says, oh no, all my other cores are not loaded enough, so let's migrate some of these threads. So it migrates 2 of the threads over to server 2, and then starts migrating it to server 3, and eventually you get a very balanced CPU consumption. And in this case, where you balance things on a more fine-grained scale, you get even more reduction in losses. So that is what I have. Basically, we've implemented the world's first series-connected server stack. I talked briefly about how I did it, the hardware that's involved, and some of the trade-offs that some of the techniques you can do to reduce the variance in power consumption. Oh, yes. Yeah.
So I have a few questions. Can you go back to the second last slide? Number 1 is 5.4x in losses of what, like the energy over that time period, or average power losses? What are we talking about here?
So I measure conversion losses for parallel configuration.
So it's energy or average power? I mean, what is
same. I mean, either energy over that time period, or average power losses over that time period.
So when you're talking about doing this balancing, like you're kind of assuming that any load that comes in can be sent to any server, like respectively of class of server, whatever. Like your analogy of looking at the cores on your CPU, like those cores have access to the same physical memory. So as far as getting the job done, it doesn't matter which core it gets sent to. But in like a real like application, when you get a request coming in, it might need to leverage like a bunch of different servers specifically. Like you have like a lot of constraints on where you can actually send the job. So can you account for that in your scheduling here? Like you're kind of just saying like I have all these available, now I'm gonna schedule it, in a way that minimizes power losses. But like in a real application, there's like so many more constraints you have to account for.
Right, and I mean, this definitely is a specific case. The specific use case here would be like scientific computing, where you have, I mean, that's the case where you use these kind of clusters. In cases where, I mean, this distributed operating system technically can work for like arbitrary kind of loads, because it does like have a share, like it has a single system image, so it sees the whole system memory. So it technically can, get memory from another server, and things will probably work. But the specific case where this really works nicely is when you have really highly parallelizable jobs that you can send out. So, you want to do some gene sequencing or something like that.
Two more questions, sorry. The first one, you started this off by saying like you're comparing it to the current topology for power. First of all, I'm curious what you mean by current. Like who uses that you're aware of?
Current?
Like you said, like each one has its own little power supply.
Yeah, this is basically standard. Basically, I think the only people that really do special kinds of architectures, like even a DC distribution architecture, like a DC distribution bus architecture, I think the big players like Facebook, Amazon, and Google are about the only people that commonly do anything special with managing the power distribution of their data.
Okay, so my second question is like, so you're comparing this to the current architecture, and the way I understand it, like the reason I choose this is because of cost, more or less. Like if you look at the cost of building a data center, the capital costs actually exceed the lifetime energy cost. So like how much extra cost are you adding because you're using like non-commodity hardware, right? Your current architecture is leveraging like the commodity everyday PSU that you get in your computer, right? Just buying a bunch of those, where you already have like efficiencies of scale and things like that. So like, is your energy savings enough to recuperate the cost? And also, how does this affect reliability? So again, we're using commodity hardware in the current architecture where they're presumed to be relatively reliable because like they're building millions of them, right? And you're going to put in something different where it seems like it's in series, right? So if something breaks in the middle, it might affect things down chain. So like this application in particular is like super, has a really big emphasis on reliability, right?
Yeah.
They really care about that, put a lot of work into it. So are you putting in places for more failures where it could be like counter to the main goals of this application? Sorry, that was a long, multi-part question.
The answer, I think that
cost and the second is reliability.
Yeah. So as far as cost goes, I definitely believe I don't have numbers right now to support this, but my intuition says definitely cost is recoverable because 8x reduction in losses is a lot. The answer to your other question is reliability is definitely a concern and is something that is on the agenda to look into. So, yeah. Professor Khan?
I do want to comment on that because it's an absolutely valid question, and yet something has changed. About 2 years ago, according to the people we talked to at Google, they did cross that threshold now where the lifetime energy cost is higher than the capital cost. So that changes a lot. I think the other thing, of course, is that right now the stuff on the left has become commoditized. There's no fundamental reason why the stuff on the right can't be as well. It's actually smaller power conversion. So it has a possibility. But absolutely, until that threshold gets crossed, it's a totally different conversation with this industry. Same thing has happened in the drives industry. Again, people have started to figure out that 95% of the cost of the drive is energy cost, and therefore they ought to be willing to spend a little bit more upfront. That threshold was just crossed relatively recently with data centers, and that is changing the conversation.
I have a question about the load balancing part. So, like when you size the regulation hardware on the right, is that dependent on how well you can do the load balancing?
Yes.
So in that case, like with the load balancing, like you can ensure maybe like 99.9% you're going to be within some like standard deviation, say, but like what would happen if you crossed into that tail region? Like would it just like explode or something?
Nope. In my current architecture, the absolute worst case would be your differential power processors would need to be able to process 2 times the amount of power. So, and probably that would be like a very transient kind of case. So I don't really even think you would need to size them 2 times. You would probably just need to size them so that they don't blow up if it needs to process that much. So, yeah. All right. Well, thank you, everyone.
Sure, where's my phone? Oh. Is it stop presenting? Yes.
Our second speaker this afternoon is Tuku. Tuku received his BS degree in electrical engineering and electronics engineering with honors from Istanbul Technical University in Istanbul, Turkey in 2009, and his MS degree in electrical engineering from UIUC in 2011, where he is currently working toward his PhD. He's been a research and teaching assistant with UIUC since 2009, and his research interests include high-performance motor drives, short-term and instantaneous torque capability and rating assessment for electric machinery, thermal modeling, and real-time hardware-in-the-loop simulation for power electronics and motor drives.
Thank you very much. Today I will talk about inverter characterization. Basically, what I have done and presented here, and maybe some of you have listened to me, was based on electric machines on specific applications, trying to understand how much peak capabilities we can get from them. Because we have this motor and it has some nameplate on it, it says this much power, this much current, this much voltage, and you just plug it in and it works. But actually there is way more behind that, where if it's rated or designed for a certain duty type, like continuous, intermittent, short-term, peak, automotive, whatever. And that actually brings in other questions as well. So basically, in most of the applications of today, where a high-performance motor drive is required, you have an inverter. And in the past, when we had dynamic applications like a traction application in a train from 1920s, 1930s, where a DC motor would be used, or any other intermittent application, you would actually use the service factor and the duty cycle to understand and maintain the motor so that it would keep working and it wouldn't be too costly to maintain, or maybe you wouldn't break it. You would like to make sure the system works fine. But now, we have a lot of other applications too. You know, like the systems are actually getting more and more advanced. We have now electric vehicles, which is actually, if you compare with the electric train in the 1920s, 1930s literatures, you have actually extreme short-term response demands in the electric vehicle. For example, in a train, you would start, it would go somewhere and then slow down, stop, start again, and keep going, right? But in the electric traction, for example, look at this. This is from the New York City driving schedule profile, at the roughly the 5th minute of it, and see the vehicle speed profile and how much current stress that actually puts on the inverter. So actually, the inverters are really pushed a lot in these applications, and there is no good way to understand how would we actually choose an inverter, or how would we design the inverter for that application. For example, certainly the inverter won't be certainly providing 300 amps continuously, but the spikes may get up to 300 amps, right? And how would I actually choose the inverter for that? If I choose an inverter rated for 300, maybe that would be too expensive. If I choose an inverter for 100 amps and try to understand if it can handle certain overload peaks, maybe I will actually break the inverter, and I need to understand, right, how this actually could be dealt with. So for example, let's look at some application of short-term overloads and transients. When we have this motor drive system, the battery, inverter, and the motor, when it's going through this drive cycle or load profile, the inverter actually has far less thermal heat storage than an electric motor does. And actually it heats up much faster and it cools down much faster as well. And so under this consideration, let's put it in a frame and try to understand. Past research actually shown that an electric machine can handle roughly 17 times its rated power for about a minute. Suppose this motor was rated for 10 amp steady state, and its starting current was roughly 6 times the steady state current, say 60 amps. So on a conventional continuous duty inverter motor drive, you would choose an inverter so that the inverter wouldn't fail under the starting of the motor, or under these short-term disturbances of start and stop cycles, right? But now I'm saying, instead of 6 times, I'm saying 17 times its rated power. It can still handle and work fine. But will the inverter be able to do that? I mean, you choose the inverter for 100 amps, we are talking about 170 amps now. How long would it take for the inverter to actually fail? So first of all, in order to understand it, we need to try to estimate the power losses in the system and run a hardware in the loop simulation in the lab. And there are many methods to actually estimate the power loss in an inverter. Well, basically need to know how it turns on, how it turns off, and how much power loss it does during conduction. There are a lot of methods using physics-based strategies like device physics equations and things, or semi-mathematical. Most literature surveys actually group them as that way, where they have combined the physics-based equations and try to create a lump parameter, a circuit model of the transistor or the power switch we are working at, and implemented in these service simulators that can be used. Or behavioral models, which is you actually are most likely to use before. Just look at these curves and try to maybe like a piecewise approximation of this voltage and current transitions and try to estimate the power loss during switching action. And that's exactly what we are doing, but in a more complicated manner from datasheet information. And we need an inverter thermal model, trying to understand for a given power loss how much the inverter will actually heat up. And basically, there are still physics-based methods using heat transfer theory, so trying to solve heat diffusion equations and things, and it's very complicated actually. Or numerical methods trying to approximate these physics-based methods using finite element or finite difference methods in a 3D geometry like this is very difficult, because for machines literature actually, there are a lot of papers trying to do finite element methods modeling, and it's actually fairly, compared to inverters, easy to actually model, because it's a physical dimension you can measure. You can go into the model, you can slice open and measure some certain parameters and dimensions, and it's just implemented. But in an inverter, it actually is very difficult because these thicknesses are in micrometer scales. and maybe widths are millimeter scale. It's very difficult to actually accurately implement these. And if you can even, any slight error in your measurements or estimations of these widths and thicknesses will actually change the performance a lot. And so basically what we do is use the thermal impedance information a lot of manufacturers provide in the data sheets. It basically tells us, if you are familiar with thermal modeling of power electronics, for example, you choose a transistor, you look at how much thermal resistance it has from its junction to its case, and then you want to attach a heatsink, and you want to know what the contact resistance is and what the heatsink's resistance to ambient heat transfer is, and that's basically a zero-order model. Well, this transient thermal impedance is actually an nth order model. For many inverters, many power switches, they provide fourth order models actually. Say you can model it as fourth order RC circuit and implement it, and it gives you a response like this, which says, well, at steady state, this is my resistance to from junction area to case, and for the diode as well. But actually, if you are going a little in a shorter duration, it actually improves the heat transfer because, well, not all the heat is actually sent out. Some of it is stored, and actually the cycle is over by the time it reaches outside, right? So basically, you can actually push it a little harder than that. And we are trying to understand how much can we push now. And basically, just the math works this way. You have this transient thermal impedance shown as Z, and then this is a convolution integral from a time varying power loss function to find the junction temperature, instantaneous junction temperature. Just to make things easier, let's assume the power is constant, and we are just applying single time bursts, like 1 millisecond, 10 milliseconds, 100 milliseconds, and trying to understand how the temperature rises. That basically comes with an equation like this, which assumes there is an nth order thermal model in a kth order inverter system, which is there are k phase legs in each heatsink. Okay, so this is basically a fourth order RC model, just for one IGBT module, one IGBT on top, one on the bottom, and two diodes, freewheeling diodes, and then we have a heatsink model here that's also modeled as an RC circuit. And these are some validation results we got from the lab, just trying to show you that this model actually works and closely tracks the heatsink temperature. And after that point, it's very difficult to measure the junction temperature, so we are using a model-based estimation, looking at the heatsink temperature, trying to estimate what the junction temperature is. So these are some initial results. Let's see what they mean to us. So on the left side, you can see these family of curves. And the only difference is in this area, which we call region 2. That means if you look at the time scale, it's roughly above 300 seconds, 5 minutes, up to infinity, let's say. And that tells me it's steady state. So basically, any kind of load in the system, if it's longer than 5 minutes, the inverter will reach its thermal equilibrium, thermal steady state. And if it's shorter than that, it has a different characteristic like this. It's a higher power dissipation capability. And above that is basically just the I squared T limitation. You just can't go beyond that because that's all the junction area can handle. But it's in the order of milliseconds, maybe microseconds. So let's think about the motor drive application we are looking at. A lot of transients actually happen in terms of seconds or maybe minutes. So basically, we are actually interested in maybe the middle of this region 1 and further. And this model tells me that the heatsink model here with different coolant flow rates where the heat transfer to ambient is improved. The only difference is in this region 2, where if it's a really bad flow rate, then it's basically a very poor heat dissipation capability. I can only run at this power level maybe, or the power loss in the junction area can be only this much. But if I improve the cooling, I can actually shift it up and maybe get a higher power dissipation capability, which means higher current handling, right? Okay. In the second part, what we are comparing is that suppose we have different heatsink heat capacities, which means the heatsink can actually store more energy for a given temperature rise. For example, if it could store 1 joule, its temperature would rise 1 degrees, let's say, and in the other case, it would actually, its temperature would rise 1.1 degrees, and so on. So it can actually store more heat per given temperature rise. It actually shows us that these curves actually shift towards shorter time scale if the heat capacity gets smaller and smaller, which means heat generated in the junction transferred to the heat sink, and the heat sink heat capacity is so small that it actually cannot handle that much, and the temperature rises really quickly. And if you have really large heat capacity, the heat sink tries to stay as cold as possible. So it seems like your base plate to heatsink junction area, or I'm sorry, the contact area tries to stay cool, and you can actually push more current in the system because the heatsink can absorb it, right? So this is pretty much heatsink's ability to absorb heat. And we can see that we can actually push the ratings towards the steady state side, which means I can actually have an instantaneous load demand or a disturbance in the system that would take 10 seconds. For the red curve, it would be a steady state rating, and I would actually need to design an inverter that's larger, or shift the curve on the right by using a larger heatsink only, but the same power switch, and I'm able to now handle much higher transients than I was able to. Now these are some experimental results on those curves. It's very difficult to measure these kind of things, so basically instead of 100 or 80 degree temperature rises, we use 10, 15, and 20. And on the left side, we are just comparing the time versus the power dissipation. And the results are roughly less than 10% for the curves, so it's good enough for our case for the future implications to be valid. And on the right side, now we are comparing the time versus the output current capability of the inverter instead of power loss. And there is one interesting result here where the solid curve is tested under 10 kHz switching frequency, and the dash curve is actually 20 kHz. I'm sorry, 20 kHz. And this actually tells me that by changing the switching frequency in the system, by reducing the switching frequency, I actually gain an order of magnitude larger time ratings, which is actually very important because in some applications, you can actually have a system where you adapt the switching frequency to the load demand you have, and still your inverter will be able to survive, even though it wouldn't be able to under a low harmonic operation, for example. And this is an interesting result. And now trying to understand,
can you just go back to the last slide quick? Yeah. So just to understand up on the left, so what you did was, let's say you looked at like 10 degrees plot.
Mm-hmm.
You commanded a certain power, so the inverter lost, let's say, like 150 watts.
Yep.
And then you measured the time that it reached 10 degrees.
Yes.
And you did it again at 140 watts, 130 watts.
Yes.
Okay.
So it took a lot of time to get these data. Please appreciate that. Especially this one. It's scale. So now let's understand how I can use this to characterize an inverter for intermittent operation, because these were actually only one-time peaks. I will apply this much power, it hits the maximum temperature in 8 seconds, and then I will stop and let it cool down. Now suppose I don't have enough time to cool down and it's repetitive, what would I do? Now, within these tests, these are the measured heatsink temperature rises, okay? So basically 20 degree rise, 15 degree rise in the junction area. How much the heatsink temperature actually rose versus time. And we can see that during regime 2, the heatsink has actually a long time. The tests take longer, or the transient or the disturbance or the peak load actually takes longer, right? Through the steady state, and the system has time so that the heat can actually go into the heatsink and be stored in the heatsink. So as you can see, as the time gets larger and larger, the heatsink temperature actually tends to rise. The heat is stored in the heatsink. But when the time is actually small, when the junction temperature hits its limit, the heatsink temperature is actually low. The heatsink didn't have time to actually heat up. Not much heat was transferred into the heatsink because of the time scale of the application. So mainly the junction temperature increased, but the heatsink temperature, the heatsink didn't even see anything changing. So this actually tells us, it gives us a good insight about how fast the inverter will cool. Actually, let's look at this. The black curves are basically peak duties in regime 2. And you can see after at some point where the system has reached steady state, junction temperature is 1 per unit, heatsink temperature is roughly 0.78, 0.77 per unit. And then we have to wait until the heatsink cools down, which takes roughly maybe 5 time constants or something like 1,000 seconds. And over here, until this point, only junction cools down, remember. So in 1 second, junction actually cools down to the heatsink temperature. But heatsink temperature doesn't change because there's a really large thermal mass. But in a peak duty in regime 1, over here, the junction temperature is 1 per unit. The heatsink is only roughly 0.05 maybe per unit. And the junction still cools down in 1 second because it's really fast. Its thermal capacity is very small. And heatsink temperature didn't even change, even though heatsink still it takes long enough to cool down from that initial temperature rise, maybe 0.5 per unit or something, 0.05 per unit. But still, now the actual job is done in the junction. See, I mean, in an application like this, I can actually repetitively apply a peak duty in regime 1, where the heatsink will not even notice that. Only the junction temperature will increase and then decrease very fast. But in a regime 2 application, even though the peaks are actually smaller, the power level, let's go back, see the power level is actually much smaller than a regime 1 application, see? I actually need to wait after the applications until the system cools down and apply it again. Whereas in the regime 1 application, the power was very high, but I can still apply it. I can still apply it more frequently. So this is actually very interesting. And how the time rating curves will look like after certain temperature rises in the junction, after a regime 1 peak duty and after a regime 2 peak duty. So basically, after a regime 1 peak duty, we still have this region, regime 1. The system actually, well, we lose the capability over here, but that's actually milliseconds, and we don't really care that much in a motor drive application, right? And we still have most of the capability here to actually apply an overload to the machine, and inverter will be able to provide that. After a regime 2 peak duty, where the system actually heated up altogether, the heatsink as well. As you can see, basically after some point, we need to limit ourselves to our steady state power limit. Otherwise, the system will burn, or the system won't be able to handle that. So when we are designing an intermittent duty application, if it's short time or longer time, these curves are actually helpful to decide how we should be choosing our device, how we should be choosing our thermal capacity in the heatsink, how we should be sizing our heatsink or the device capabilities. So now let's try to move into a different application where these were actually one-time bursts, as I said, or intermittent application. But how would we use those curves to actually rate an automotive duty application? Because, well, systems are more random. You cannot generalize them that much. There are some drive cycles to actually test our systems, maybe. And here are two. Highway fuel economy test here, you can see, and the UDDS driving schedule. And as you can see, there are a lot of starts and stops here that actually put a lot of thermal stress on the inverter and the machine as well, because the system will be under thermal and mechanical stress the most in an acceleration or deceleration, because it produces positive or negative extreme torques. Whereas in a steady state or constant speed operation, it doesn't suffer that much, because the only thing motor is trying to do work against is the drag force, the airflow on the vehicle, right? And basically that's not as much as if the motor was trying to accelerate the vehicle against that airflow as well. So it's basically start and stop cycles are much more thermally destructive than. And this is the temperature profiles under those tests, for example. So you can see the system is roughly 80 degrees hot maybe, and then after a peak happens, it rises up to 140 degrees, 130 degrees, and then cools down really fast. Or in the UDDS, it's even more frequent than that. So how do we actually understand? We have this module, power module. How do we understand if it's going to work? And because basically, if you think about it this way, you have this power module, you are using it, it's supplying current. And as it's supplying current, it's losing its ability to supply more. It's losing its ability to overload because you are using its thermal storage, right? And when I reach this point, how am I going to know that the inverter didn't actually lose its capability to provide me this much, temperature rise, okay? So first of all, to do that, let's, because it's not generalizable easily, let's look at this drive cycle energy. Basically, looking at this example power loss waveform here, over here, and the temperature that our thermal model tells us, we can actually populate energy trajectory, the safe operation trajectories. For example, we can just look at these curves, and whatever junction temperature we are at instantaneously, we can actually calculate how much energy the system can handle at that point. And also integrate the drive cycle power throughout the drive cycle, basically, and then come up with the energy requirement, the energy loss requirement, the energy loss that the drive cycle will put on the inverter. And populating those trajectories from the thermal capability curves I showed here, from the intermittent ratings with an initial temperature rise, a maximum allowable junction temperature rise, and time, we can actually calculate safe trajectories. And one law, the safe trajectory has to be above the energy capability and the energy requirement curve that the drive cycle enforces us. So basically, if it's below, then the system will actually exceed the maximum allowable temperature rise we defined here. And this is for a 50-degree temperature rise populated curve, for example. And we can see the system actually exceeds 50 degrees right around here. And we can see that actually curve tells me, and also tells me that the slopes between these two curves tells me how much thermal reserve I have in the inverter as well. So basically, it's more like we still need to know the temperature of the system through a simulation, but it also tells us how much heat reserve we have in the system, and we can still keep pushing it. So basically, we can use this methodology to protect the drive if we are the user, if we know the heat storage, how much thermal reserve we are using. We can protect the system, or we can actually know how much remaining thermal reserve is in the system and try to understand if it's an over-design or under-design. And if we are the designer, we can actually modify the design according to these curves. And another example is a fault duty application, for example, where this inverter actually, it's a hex bridge, it blew up. One IGBT here, one IGBT here. It's spread around all the. We have another one in the lab actually. So in 50, and if you'd like to see, I can show you one. So basically, these time rating analyses can tell us when the system is, for example, let's think about a scenario where the system is working and the motor drive is going under a certain disturbance or some fault maybe, and the current actually increased a lot. And now the inverter was designed for a certain operation, and the maximum current maybe is exceeded, and the temperature started to rise. And it took roughly half a second to compensate the fault. We can actually know how much the temperature will rise during that fault duty. This can be a motor drive broken rotor bar, or maybe one of the phases was lost and only two-phase operation was required on the motor, so that you can safely drive it somewhere and then turn it off and maybe have a maintenance. And this analysis can also tell us how much the system will perform, or if it will be able to handle certain fault duties, and time to clear a fault, basically. So my conclusions are, inverters are not as forgiving as machines under overloads. We need to look at them carefully and try to rate them based on their thermal storage, and try to be a little clever about how we manage that thermal storage, because even though the machines can handle certain overloads very easily, the inverters will not be able to. And we looked at methods, how can we actually make an inverter to handle certain overloads? By changing the attached heatsink thermal capacity, the flow rates on the heatsink, or the cooling performance of the heatsink. And basically, the populated curves were shown to be used in repetitive duty characterization or under periodic loads in automotive duty, for example, and fault tolerance of a drive. I can take any questions if you would. Yes.
Hey, Tuku, your first bullet on your conclusion slide is not as forgiving a machine. Is that in a thermal management sense?
Yes.
So in other words, is there a difference in energy density in terms of heat? I mean, if you make the inverter overcome that one,
Excuse me, if you make the inverter?
if you increase the size of the
Oh, yeah.
inverter,
Yep, so yeah, basically, but then we have to be very careful. Are we over designing the system? Because if you look at these curves again, the inverter will reach 130-degree temperature rise, maybe 140 temperature, only once during the drive cycle. If you choose an inverter to actually handle that much power, there's an extensive power loss on the inverter junction here. If you choose the inverter to actually handle that continuously, you make the inverter really big, then the system temperature rise won't even reach that temperature, right? The system won't reach that temperature because the system is able to continuously handle that up to some temperature. But now the system will be over-designed because the mean temperature in the system will be maybe 30 degrees. The inverter won't even heat up, and you will not be using your entire thermal reserve if you make the system big. So we are now trying to look at if the system is not oversized, maybe not undersized, what would be the best way to actually choose an inverter, make the size the inverter so that the system will actually survive certain overloads. Of making it bigger is always an option. We are not trying to follow that though.
Have you looked at how industry does it in current practice, and do they just oversize curves?
Well, so by industry, I can compare some of my results with the commercial inverters we get here, and basically they have certain overcurrent protections, where if a certain current, for example, 10% of 110% operated is reached, it has certain time to actually cut the system power or shut off the system. And I haven't seen any example of an application like this in an actual existing inverter, but it's not too difficult to think why not. That might be.
Tuku, how does that affect the mean time between failures, like shortening the lifetime?
That's future work. Well, basically, there are the lifetime of the inverter depends on two factors. Well, basically one factor. There are these bond wires, right, connecting the junction to the outside terminal, and that bond wire is everything. If you lose that bond wire, then the inverter is assumed to be, I mean, there are multiple of them due to redundancy, and after some number of them has failed, the inverter is assumed to have failed. And they are soldered to the junction area, and this entire junction here is soldered down to the copper base plate. So there are two things. If we go back to this curve, an inverter is a power cycle, extreme power cycle, fast power cycle, that would be considered regime 1, where the junction temperature rises a lot and then goes down a lot. Heat sink temperature doesn't change. So basically the enclosure temperature doesn't change. It's not a thermal cycle, it's a power cycle. Regime 2 case, it has a thermal cycle as well. The heat sink heats up, the case heats up a lot, and then it cools down, and then heats up again and cools down. So basically, in regime 1, where the system is actually heating up really fast and cooling down really fast, these bond wires are affected the most. And there are certain curve fits that the industry provides us about the failure rates under a power cycle like that, where these bond wires expand, contract, and the solder contact area just breaks, and then you lose the bond wire. In the second case, where there is a thermal cycle in the case, that affects the junction solder between, well, this IGBT and the copper base plate. That means if you lose, if your solder area is damaged, that means you don't have good contact with the base plate anymore. which means you cannot dissipate enough power to the ambient anymore. That means your junction temperature will rise more than what it would when you just first bought the device, right? And that would mean the system will overheat again and the bond wires will fail again. So that's a failure due to thermal cycling. Both failures are basically because of bond wire melting down or the system. If there is something extreme like this where the IGBT junction actually blows up, that's a total different story. But these characteristics, how each would affect the system reliability is like this. The regime one would affect the bond wire directly, where the heat transfer from the junction to the heatsink hasn't changed much, and the thermal cycle where regime 2, the steady state is reached. That means the entire system heats up and cools down, which means the thermal contact between the junction and the base plate is damaged, fatigued maybe, and then that would actually cause an excess temperature rise in the junction and lose the bond wire. And so I don't have numbers for that, but many manufacturers provide different curves and different characteristics, so it's real difficult to generalize. I hope that answered your question. Any questions? No? Thank you very much.
So here? No. So here, like, you don't mention the series spec of this machine.
Okay.
You know, like, this is for recording here.